Okay, in this lecture we're going to cover the first part of our section 1.2 material on the calculus of parametric curves. So let's start this section by posing a question. Suppose that we have a parametric curve, let's call it C, which is defined by the parametric equations x is equal to x of t and y is equal to y of t. So recall these parametric curves are defined using parametric equations if we're not necessarily able to define our curve as the graph of some function. So for a given curve in the plane, a question of interest from Calculus 1 was what is the slope of the tangent line to this curve C at a given point. And we saw in Calculus 1 that the slope of the tangent line to a curve, which is the graph of a function, is given by the derivative of that function. However, if we have a parametric curve, which is not necessarily the graph of a function, how can we find the slope of the tangent line, or the derivative to this curve at a given point? So the answer to that question is given by the following theorem. So this gives us a formula for the derivative of a parametric curve, or derivative of parametric equations. So let's consider the following. Suppose that we have the parametric curve defined by the equations x of t and y of t. And let us suppose that both x prime and y prime of t exist, and that the derivative x prime of t is non-zero. So I claim that the slope of the tangent line to this curve at a given point, which we know is given by the derivative dy dx, or the rate of change of y with respect to x, is given by a ratio, where our numerator is the derivative of y with respect to t, or if you prefer, simply y prime of t, divided by the derivative of x with respect to t, or if you prefer, simply x prime of t. So let's take a look at a quick proof of this theorem. This result follows directly from the chain rule from Calculus 1. So by making use of the chain rule, if I'm differentiating y with respect to t, and y can be thought of as a function of x, then I could get the derivative of y with respect to t by first differentiating y with respect to x, but since x is a function of t for a parametric curve, I would then have to multiply by the derivative of x with respect to t. So recall this is the Leibniz form for the chain rule. So in the event that x prime of t, or the derivative of x with respect to t, is something other than 0, then I can take this equation and divide both sides by the derivative of x with respect to t. And what we have is the derivative of y with respect to t divided by the non-zero derivative of x with respect to t is equal to the derivative of y with respect to x, which is the result that we wanted to establish. So now we have a way to find the slope of the tangent line to a parametric curve, making use of this new formula. So let's look at an example of this. In our first example, we're asked to calculate the derivative dy dx for the parametric curve defined by the equations x of t and y of t, where t is within the interval from -2 to 3, and we're asked to locate any critical points on the graph. So let's start by finding our derivative. That's the first part of this problem. Find the derivative dy dx, which using our new theorem is found by taking the ratio y prime of t over x prime of t. So for our numerator, taking the derivative of our function for y, we have y prime is 6t squared minus 6, and then we divide by the derivative of x, which is 2t minus 4. So this is the first part of this problem, is find that derivative of y with respect to x. So now, the second part of the question is to locate any critical points on the graph of our function. So recall that critical points are points on the graph of a function or on a curve where the derivative is either 0 or undefined. So I'll mention here that to find our critical points, we're looking for points at which our derivative, dy dx, is 0, or where our derivative dy dx is undefined. All right. So the first type of critical points which I could have are points for which the derivative is equal to 0. So let's look for those. We're going to take our derivative, dy dx, which we just found to be 6t squared minus 6 over 2t minus 4, and we're supposed to set it equal to 0. Now, the only way that a fraction can be equal to 0 is if our numerator is 0. Or in other words, we can multiply both sides through by the denominator, 2t minus 4, and we have 6t squared minus 6 is 0. Or dividing through by 6, we have t squared minus 1 is 0. So t squared is 1, and t would be plus or minus 1. Now, the other type of critical points which we could have would be points for which our derivative dy dx is undefined. Now, the only way that this derivative can be undefined is if we have division by 0. So we know that if we have a denominator of 0 for this ratio, then the derivative dy dx is then undefined. So to look for this other type of critical point, we're going to set our denominator, 2t minus 4, equal to 0, and we find that 2t has to be 4, and so t is 2. Now, in the problem statement, we were asked to locate the critical points on the graph of our function, not the values of t for which critical points occur, but the actual points themselves. So to find the points on our curve, we need to take these t values and substitute them into the equations for x and y. So let's start with our first value of t that we found. T equals 1. So if t is equal to 1, then x and y can be found directly from the parametric equations in the problem. So if t is 1, x would be 1 minus 4, or negative 3. And if t is 1, then y would be 2 minus 6, or negative 4. Now, for the next value of t that we found, t equals to negative 1, we would have the point xy on our parametric curve given by, so let's see, x would be 1 plus 4, so 5, and y would be negative 2 plus 6, so positive 4. And our last critical point would correspond to the value t equals 2. So if t is 2, then the corresponding point on our curve would have an x-coordinate of 4 minus 8, so negative 4, and y would be 8 times 2 is 16 minus 12, would be positive 4. So altogether we have 3 critical points. The first 2 are points where our derivative is 0, so we would have a horizontal tangent line on our curve. And the third critical point, when t was equal to 2, has a derivative which is undefined. So on the curve, we might have a vertical tangent line, we might have a sharp corner somewhere in the graph, or a discontinuity at that point where our derivative would not exist. Okay, so let's look at some other examples. In this next example, we are asked to find the equation of the tangent line to the curve defined by the equation x of t and y of t at the point where t equals -1, and we want to express our answer in slope-intercept form. So here, in order to find the equation of a line, we need 2 things. We need the slope of the line. So for the slope of the tangent line, that would be the derivative. And we need a point on the line. So here, let's start by finding a point on our line. And we're told here that we're interested in the point corresponding to t equals -1. So let's find that point first. So if t is equal to -1, then the point of interest on our curve is the point xy, where x would be -2 plus 3, so +1, and y would be t to the 4th, so -1 to the 4th is +1. So our tangent line will pass through this point, 1, 1. And we also need the slope of the tangent line, which is our derivative, dy dx, which, using our new theorem, is found by taking the ratio y prime of t over x prime of t. So here, our numerator, y prime, is 4t cubed. We're dividing by x prime, which is 6t squared. So simplifying a little bit, the ratio of our constants, 4 over 6, reduces to 2/3, and then we have t cubed divided by t squared, which leaves us just t to the 1st power. Now we're interested in the slope of the tangent line at this specific point where t is equal to -1. So again, if t is -1, then the slope of our tangent line, which is the derivative dy dx, is 2/3 t, so we would have a -2/3. So now that we have the slope of the line and a point that the line passes through, we can find the equation of the line by using the point-slope form for the equation of a line, which would be given by y minus the y-coordinate for the point on our line, which we found to be 1, is equal to the slope, which we just found to be -2/3, times x minus the x-coordinate for the point on our line, which was also 1. Now, in the last part of the problem, we're told to express our answer in slope-intercept form. That is the form y equals mx plus b. So in other words, we just need to solve this equation for y. So simplifying a little bit, we have y minus 1 is equal to -2/3 x plus 2/3. And then adding 1 to both sides, we have y is -2/3 x plus 2/3 plus 1 would be 5/3. So in these last two examples, we're seeing how to find the derivative for a parametric curve. So that is the slope of the tangent line to the curve at a point. And in this last example, how to find the equation of the tangent line to that parametric curve at a point. So let's look at another example. In this next one, we'll illustrate something that's interesting and kind of unique to parametric curves. So here we're asked to find the points on the curve defined by the equations x of t and y of t, where the tangent line is either horizontal or vertical. So to determine where our tangent line is horizontal, we need to know where the slope of the tangent line, or the derivative, would be 0, since a horizontal line has 0 slope, or where the tangent line is vertical, which would mean that our derivative, the slope of the tangent line, would have to be undefined. So it's very similar to the example that we looked at earlier. And you'll notice in the notes here, I've given a graph of this parametric curve, which you could obtain yourself by using that Desmos plotting program that I mentioned at the end of the section 1.1 lecture notes. So here we're going to find these points algebraically, and then we can verify our results using this graph and see something kind of interesting that happens. So our first step is to find the derivative, which represents the slope of our tangent line. So we start by considering the derivative dy dx, which is defined as the ratio y prime of t over x prime of t. So here our numerator, y prime, would be given by 3t squared minus 3, and our denominator, x prime, would be given by 3t squared minus 6t. So we could say that our tangent line is horizontal if our derivative, dy dx, which we just found to be 3t squared minus 3 over 3t squared minus 6t, is equal to 0. So again, as with our earlier example, the only way that a fraction can equal 0 is if our numerator is 0. So we have 3t squared minus 3 must be 0. Or if we divide the equation through by 3, we have t squared minus 1 is 0. So t could be positive or negative 1. So again, we were asked not just for the values of t, where our tangent line is horizontal, but the actual points on the curve where we had a horizontal tangent. So we need to take these values for t, namely t equals 1 and t equals negative 1, and find the corresponding point on our curve, xy. So in the event that t is 1, then substituting into our parametric equations, we find x would be 1 minus 3, or negative 2, and y would be 1 minus 3, so also negative 2. And if t is negative 1, then the point on our curve, xy, would be given by negative 1 plus 3, or excuse me, negative 1 minus 3, so negative 4, and y would be negative 1 plus 3, so we get a positive 2. Okay. Now we were also asked for points where our tangent line is vertical. So we would say our tangent line is vertical if the derivative dy dx is undefined. Remember, the slope of a vertical line is undefined. So if the tangent line is vertical, the derivative, which is the slope of the tangent line, would need to be undefined. So looking back at our earlier work, we found the derivative dy dx to be the following ratio. And the only way that this ratio would be undefined is if we have a 0 for our denominator. We know that division by 0 would be undefined. So to determine which points on the curve have a vertical tangent, we're going to take our denominator, 3t squared minus 6t, and set it equal to 0. So solving for t, well, we see that we could factor out a 3t from each term, and we're left with a t minus 2 is 0. So we have two choices. Either t is 0 or t is 2. Now again, we need to find the points on the curve corresponding to these values of t. So let's look at the first one. If t is equal to 0, then the corresponding point on our curve, xy, would be 0, 0, the origin. And if t is equal to 2, then we have the point xy on our curve would be, let's see, x is 2 cubed or 8 minus 12, so negative 4. And y is 2 cubed or 8 minus 6, which would be 2. So we found the following 2 points where we had a horizontal tangent, and we found these 2 points where we had a vertical tangent. Now, if you compare these answers, you might notice something a little unusual. There's one point, namely the point negative 4, 2, where our tangent line was horizontal and vertical. So we might ask the question, well, how is that possible? What would that mean here? So let's verify our results using our graph and take a look at this point where we would have 2 different tangents. So starting with the points where we have a horizontal tangent, we saw we had that at the point negative 2, negative 2. So that would be the following point on our curve, and we see that we do indeed have a horizontal tangent line there. And at the point negative 4, positive 2. So that is this point here, where we do indeed have a horizontal tangent. Now, the case of a vertical tangent, we had at the point 0, 0, that is the origin, right here. We see that the tangent line to our curve is indeed vertical. And also at the point negative 4, 2, the same point that we had before here, we see that our tangent line to the curve would be vertical. So this illustrates sort of how that's possible. We have a parametric curve here, which is self-intersecting. It passes through the point negative 4, 2 at 2 different times. At the first time that let's sketch this in, our object is traveling in this direction, so we could add little direction arrows to indicate the orientation. And we see that the curve intersects itself at this point, negative 4, 2. So the first time that our object passes through that point, we have a horizontal tangent line to the curve at that point. And at the second time that our curve passes through that point, we have a vertical tangent. So this is something that's kind of unique to parametric curves. We certainly wouldn't see that for a curve which is the graph of a function because it couldn't be self-intersecting. All right, so let's look at some other questions of interest. So we've been working with finding the tangent line or slope of a tangent line to a parametric curve, which would be given by the first derivative. Now, another question of interest for parametric curves might be determining their concavity at a given point. Are these curves sort of upward opening or downward opening? And that information is given by the second derivative of a function which defines the curve. So how do we find the second derivative for a parametric curve? Well, we have a formula given by the following theorem. So this is a formula for the second derivative of a parametric curve, or a parametric set of parametric equations. So here, let's suppose that we have equations x of t and y of t, which define y as a twice differentiable function of x. And let us suppose that the derivative of x, or the parametric equation for x, is non-zero. So the second derivative of y with respect to x, which would give us information about the concavity of a curve, is defined as the derivative of the first derivative, dy dx. So we're taking dy dx, our first derivative, and then we are differentiating that with respect to x. So using the same formula that we had for the first derivative of a set of parametric equations, well, we know how to find the derivative of a parametric curve. But now the function that we're differentiating is now the first derivative, dy dx, instead of just y itself. So we take the same formula that we had in our previous theorem, but we replace y by the derivative of y, that is y prime, or really, to be a bit more precise here, our numerator is found by taking the derivative of our first derivative, dy dx, but with respect to t. And then we're dividing by the derivative of x with respect to t. So this is the exact same formula that we had for the first derivative, but we're replacing y by the derivative of y with respect to x in order to get that second derivative. So now that we have this formula, let's look at some examples making use of this. So in our next example, we are asked to find the second derivative of y with respect to x as a function of t if we have the parametric equations x of t and y of t given here. So in order to find the second derivative, well, we have to find our first derivative. So let us start by finding the first derivative, dy dx, which we've already seen is given by the ratio y prime of t over x prime of t. So for our numerator, y prime, we have 1 minus 3t squared. And then we're dividing by x prime, which would be 1 minus 2t. Now, once we have that first derivative, this new theorem says, okay, well, for our numerator, we have to take that first derivative that we just found and then differentiate that with respect to t. So let's take a look at that. So in order to differentiate the expression that we just found right here with respect to t, we see that we're going to need to make use of the quotient rule. So I'll say by the quotient rule, if we want to differentiate the first derivative, dy dx, with respect to t, we first take the derivative of our numerator, which is negative 6t, times the denominator, 1 minus 2t. And then we subtract the product of our numerator, 1 minus 3t squared, with the derivative of the denominator, which would be negative 2. And then the entire expression is divided by the denominator squared. So let's simplify a little bit. In the numerator, distributing the negative 6t, we have negative 6t plus 12t squared. And then we are subtracting, if we distribute the negative 2, we have negative 2 plus 6t squared. The entire thing is still being divided by 1 minus 2t squared. So now, combining like terms, we have a 12t squared. We're then subtracting 6t squared, so that leaves us 6t squared. Then we have a minus 6t. And then we are subtracting a negative 2, which is the same as adding 2. And the entire thing is then divided by 1 minus 2t quantity squared. So what we found now is the derivative of our first derivative with respect to t, which is just the numerator for the second derivative expression. Recall, we still have to divide what we just found by dx dt. But notice, let me use a different color here. So this denominator, dx dt, we actually already found in our earlier work. When we found the first derivative, our denominator was x prime, or dx dt. So let's write out our answer. We have the second derivative of y with respect to x is given by, writing out our formula again, we take the derivative of dy dx with respect to t, and then we divide by the derivative of x with respect to t. So our numerator is the value that we found, 6t squared minus 6t plus 2 all over 1 minus 2t squared. So that was what we just found using the quotient rule. And then we're supposed to divide that entire expression by the derivative of x, which in our earlier work we already found was 1 minus 2t. So simplifying a little bit, well, if I take this fraction, where my denominator is 1 minus 2t squared, and I divide by 1 minus 2t again, then my denominator is 1 minus 2t cubed. And my numerator is still 6t squared minus 6t plus 2. So this would be our expression for the second derivative of that parametric curve y with respect to x. And this second derivative can tell us some information about the concavity of that parametric curve. So let's look at one other example illustrating some applications of the first or second derivative for a parametric curve. So in this next one, we are asked to consider the parametric curve defined by x, which is t plus e to the t, and y, which is 1 minus e to the t. And in part A, we're asked for an equation of the tangent line to the curve at the point where t is 0. So again, to find the equation of a tangent line, or any line, there's two things that we need. The slope of the line, so for the tangent line, that is the derivative, and a point that the line passes through. Now we're told in the problem we're interested in the point where t is equal to 0. So let's start by finding the point on our curve. So here, if t is equal to 0, then the point on our curve, xy, would be given by, so x is 0 plus e to the 0, which is 1. And y would be 1 minus e to the 0, which is 1. So 1 minus 1 gives us 0. And to find the slope of our line, well, the slope of the tangent line is the derivative, dy dx, which for parametric curves is found by taking the ratio y prime over x prime. So our numerator, y prime, is negative e to the t, and our denominator, x prime, would be 1 plus e to the t. All right. Now we're interested in the derivative at a particular point, namely the point where t is equal to 0. So if t is equal to 0, then the slope of our tangent line, which is the derivative, dy dx, is given by negative e to the 0, so negative 1, over 1 plus e to the 0, so that would be 1 plus 1, or 2. So our slope for the tangent line is negative 1/2. So now that I have a point on my line and its slope, I'm ready to find the equation of the line using point-slope form. So we would have y minus the y-coordinate for our point, which was 0, is equal to our slope of negative 1/2 times x minus the x-coordinate for the point that the line passes through, which we found to be 1. So simplifying just a little bit, we have y is equal to negative 1/2 x plus 1/2. So this is the equation of that tangent line to the curve in slope-intercept form. Now in part B, we're asked to find the second derivative of y with respect to x, also at the point when t is equal to 0. So in order to find that second derivative, let's think about our new theorem. So here, again, in order to find the second derivative of y with respect to x, our new theorem says we first take the derivative of the first derivative, dy dx, but with respect to t, and then we divide by the derivative of x with respect to t. So for our numerator, we're going to take the first derivative, which we already found in part A, it was this quotient, and we have to take its derivative with respect to t. So as with the last example, we see that we need the quotient rule here. So by the quotient rule, the derivative with respect to t of our first derivative, well, we start by taking the derivative of our numerator. So the derivative of negative e to the t is negative e to the t, and then we multiply by the denominator, 1 plus e to the t. Then we subtract the product of the numerator, which was negative e to the t. So since we're subtracting that value, this becomes a positive e to the t, times the derivative of our denominator. So the derivative of 1 plus e to the t is just e to the t. And the entire expression is then divided by our denominator, 1 plus e to the t squared. So simplifying a little bit, let's see what we're left with. So we have a negative e to the t minus e to the t times e to the t, which is e to the 2t, and then plus e to the t times e to the t, which is e to the 2t, over 1 plus e to the t quantity squared. So we see here that in our numerator, the positive and negative e to the 2t cancel, and so we are left with just, let me squeeze this in for room, negative e to the t over 1 plus e to the t quantity squared. So now, what we just found is only the numerator for our formula for this second derivative. We can't forget we still have to divide this expression by dx dt, but we've already found dx dt. In part A, when we found the first derivative, our denominator, x prime, is the derivative of x with respect to t. It's 1 plus e to the t. So if I take the expression that I just found, which has a denominator of 1 plus e to the t squared, and I divide by 1 plus e to the t again, then my second derivative of y with respect to x is negative e to the t, now divided by 1 plus e to the t quantity cubed. So we're interested in this second derivative at the point when t is equal to 0. So let's finish out this problem by evaluating at t equals 0. So here, if t is 0, then our second derivative of y with respect to x is given by negative e to the 0, or negative 1, divided by 1 plus e to the 0, so 1 plus 1, or 2 cubed. So 2 cubed would be 8. So this is the value that we're interested in. And now what does this tell us about our curve? Well, the fact that this second derivative is negative 1/8, which is negative, that means that our curve has a concave downward shape at the point where t is equal to 0. So we can use this second derivative to gain some information about the shape of our curve, in particular its concavity.